Hi everyone, thank you for registering for this online workshop, Help Build the Next Generation of Predictive AI KumoRFM Beta. I'm Katie Jovanovska and I will be your host today. Before we begin, I'd like to say thank you for joining the Kumo Beta community. We're excited to have you on board and can't wait to see what you can build with KumoRFM. In this KumoRFM Beta session, you will have the chance to hear from Matthias Fey, founding engineer at Kumo, and Vid Kotsian, ML engineer at Kumo. Today, they will cover how to predict anything from your business data instantly, how to skip the heavy lifting of data science, and turn business questions into predictive answers. Before we begin, please remember to use the Q&A section to ask any question throughout the session. During the beta session, we will answer your question and give your feedback live. And now I would like to invite Vid to open the session. Vid, over to you.
Thank you, Kitty, and thanks everybody who joined. So everybody who is attending this call probably heard already about KumoRFM. So I would like to be brief with the introduction, not to waste way too much time on concepts that you're already familiar with. So let my introduction be a brief refresher. So what is a Kumo foundational model for prediction? Just like large language models that we are all familiar with by now, make predictions with in-context learning from the context text, so reading text and predicting more text, the concept of KumoRFM is to generate to unseen examples in tabular machine learning by learning from examples provided in context. So in the example given on screen, we are basically predicting the amount of sales, so the number of sales in the coming 30 days with for customers who have had at least 90 days, who have been active in the last 90 days. The core idea being that the foundation model takes a couple of examples from the past as part of the input and makes the prediction without training a whole new model from scratch, saving us a lot of resources and especially time. So, as already mentioned, in traditional modeling, we would train a new model for every use case. We would create and train weights from scratch, and then use this frozen model to make predictions. And then in KumoRFM, the main difference is that we have a frozen model at all time. And by skipping this training, we can make these predictions like this cycle significantly faster, as it's done as part of a single forward pass. And so this relational foundation model needs to be quite robust. So it needs to handle not just different use cases, but also different databases, different data types, and data can be incredibly semantically different. So we need to handle data from e-commerce, from finance, from healthcare, and other use cases that might not have appeared during training time. Similarly, each of the use cases on these very different areas differ from something that might seem simple on the surface, such as what is a transaction fraudulent, so something like value imputation, to something more complicated, such as forecast demand over time. And finally, we have designed our relational foundation model to not only handle this very diverse data and diverse queries, but to also provide explanations and evaluation to allow you to reliably use it and to trust the output. So the mental model, when using the KumoRFM, comes in these two major steps. So how to sort of think about the data and think about the setup when trying to use KumoRFM on your own individual use case. So data does not require major pre-processing. However, it needs to be provided in a standardized way. So data is a set of tables connected by keys to form a graph, with every table being annotated with primary keys and foreign keys that denote connections between tables, and any table that contains facts annotated with a timestamp. And these tables are connected by connecting their corresponding primary and foreign keys. And then we've got the prediction step, where we write a query using our own internal predictive query language, which is sort of vaguely inspired by SQL and describes what you're trying to predict. So in the examples given on the screen, we are predicting, for example, the count of whether a count of orders for a user is going to be larger than 0 in the coming 7 days. That is, if the customer is going to make a purchase or not, or what the sum of all of their predictions or orders is going to be. So these queries are written relative to a specific prediction time, which is then going to be moved around and used by the system to generate context data that is then used as part of the input to the model and to make the prediction for the future. So under the hood, what KumoRFM will do is we will have this massive pre-trained graph transformer that will encode and learn the representations across multiple tables and across multiple of context examples, and then generalize from the in-context examples to the example of interest. So specifically predictions for users provided as part of the query, or entities in general, not necessarily users. With this, I would like to pass over to Matthias, who will be talking more detailed about how to use Kumo, or also how to use Kumo SDK. Matthias, over to you.
Okay, thank you, Vit, and thank you everyone for joining to this European beta session. And so yeah, my name is Matthias Frey. I'm founding engineer at Kumo, creator of PyTorch Geometrics. So I'm in graph machine learning for a long time. And today we are super excited to let you beta test KumoRFM and what we built on over the last months and years. So we released early stage of KumoRFM, which is ready to be installed via Python. You can simply do that with pip install Kumo AI. And we also host this website called KumoRFM.ai, which holds quick start guidance, call-up notebooks, playgrounds, API keys, and so on. So feel free to check that out. In the end, Kumo AI or the Kumo SDK Python package is designed to have full support for Google Colab, Jupyter Notebooks, or IDEs wherever you want to code away. And then there's no major other dependencies besides NumPy and Pandas, so it shouldn't conflict with any of your dependencies. Yeah, we tried our hardest to keep the dependencies to the lowest amount possible. So KumoRFM or the KumoRFM package works by having a client and server model. And so the main idea is that inside the client, inside your local machine, you prepare the data you want to input into KumoRFM. And the way you can do that is via pandas data frames. So in the end, we're working on relational data here. So we have multiple tables we can load as pandas data frames, and then we can simply write them into a dictionary where the key denotes the table name and the value holds the table data corresponding to this table. And so based on this, you can now define a graph schema definition. And so you can define how the metadata of each table looks like. For example, what is the primary key of that table in case it exists? What is the time column or the create time of this table in case it exists? And especially how different tables are interconnected to each other. Afterwards, we go ahead and materialize your graph, and that is we bring it into a format where we can efficiently query context from it, where we can efficiently compute subgraphs from it, and so on. And so that's all you need to do. This is a one-time step or a one-time setup. And then once you have your model up and running, you can now query it using our predictive query language that we introduced earlier. So you can type different predict commands similar to how you would query SQL. And these predict commands gets passed and validated and are then used to generate the context for this in-context learning model. And so what that means is that we're generating context from the past. So we're querying historical subgraphs and historical labels corresponding to these subgraphs. And then we query the subgraphs for the entity we want to make a prediction for at a specific point in time. And then this context is used to derive a prediction for this entity we are interested in. And so only this minimal set of information is actually sent to our model to make a prediction. The model is executed on the server and sends a result back. So this whole procedure is basically built with security in mind. We have like a stateless server that doesn't store anything, so you don't need to upload your data or your full data. And then only the minimal context is actually being shared across client and server here. And so I want to give a quick introduction on how this whole KumoRFM package actually works. And so there are two key steps. One is you need to create your graph, and then the other step is how you can actually make predictions. And so the step one is, as I said earlier, you can import your data as a set of pandas data frame objects. And then you load this in-memory data into Kumo and double check the inferred metadata. And especially what to look out for are here the primary keys, and primary key refers to like a unique identifier of each row. And this primary key is used to be able to connect to different foreign keys in other tables. So we're defining a link here, but it's also used as an identifier for making a prediction for a specific entity. So for all the entities you input into KumoRFM and you want to make a prediction for, it is required that these entities also have a primary key. And then another important notion is the definition of a time column. And the time column are especially important in like fact tables, such as what did the user order for items, or which items did the user look at, and so on. And so usually these come in the form of having like a temporal facts where we have like specific points in time where these interactions have been made. And these definition of time columns help us to be aware of temporal consistency. So if we go back in time, we make sure to only look at the facts that are available at this point in time. And the third thing to look out for are the column semantic type. And these column semantic types basically define how different columns are used as features in your model and are used inside the model downstream. And so they are especially important for column encoding. And there's a difference between whether you represent a column as like a categorical value or as a numerical value or as like a column holding text or embeddings and so on. So always good to look out for. And then the other thing where this is used is to define like the type of prediction we want to make. And so if you have like a numerical column and you want to impute missing values from this column, this is inferred as a regression task. But if you have like a categorical column and you want to impute missing values from there, this is interpreted as a multi-class classification task. And so in the end, KumoRFM is designed to be quite simple to work with, and so we added a lot of logic to infer these primary keys, time columns, and semantic types from scratch. And if you write this code block here shown down below, then all of this information we will try to infer from scratch. And so how do we do that? So in the end, KumoRFM comes with a link inference logic, a type inference logic, and so on. And so whenever we want to infer primary keys, we do that based on name matching. So if we have like a table called users, then we directly know that something like user ID needs to be a primary key in that table, but we're also being a bit more sophisticated here in the sense that we check for fraction of unique values and so on to make sure that the primary key we infer is actually correct. For time columns, we infer that based on the ability to be passed to like a date-time compatible format. And then for graph links, we infer different columns and their links to primary keys based on name matching. So if you have like an orders table that holds like the column user ID, it's directly easily inferable that we need to match this or link this column to the users table. But we're also checking for value overlap and many other things. So in like 90% of cases, this is all you have to do, and everything works out quite well. In the other 10% of cases where you have like super hard to detect primary keys because you have a lot of duplicate values or NA values, and if the name matchings do not align with what you think is good, then you can also directly and conveniently change that by yourself. So you have this graph, and you can index tables in that graph using like the classic Python notation of the square brackets here. So if you index graph users, that will give you the user table. And then if you index once more, like the age, then that gives you the age column. And you can change like the semantic type of that column. And different semantic types are available here, such as numerical, categorical, multi-categorical, and so on. And so you can do the same for like primary keys and time columns as shown here. And then you can also link tables together by specifying like the source table, which is like the table that holds a foreign key. You specify the foreign key, like this is the column inside the source table that holds this foreign key data. And then you specify the destination table, which is like the table you link to, which holds the corresponding primary key. Okay, once you have your graph set up, we make KumoRFM as easy as possible to then make predictions right away. And there exist two steps in order to make a prediction here. And so all the predictions you can do are based on this predictive query language interface. So you actually need to think of two steps in order to make a prediction. So the first step is, what is the entity you're making a prediction for? So for example, in our case, this could be the users table to infer something like user age or whether the user will churn. Then the entity you're making a prediction for will be the users in this example. But you can also think about making like the orders table the entity in case you want to predict like the amount of that order that was bought, or whether you want to classify this order or transaction as fraudulent or whatever. And then in the second step, you are then ready to define the target you want, or the label you want to predict for this given entity. And so you can define this target based on the entity table itself, in which case we refer to that as missing value imputation. But you can also create targets of one hop away fact tables, in which case we refer to that as temporal forecasting. And that means, for example, you can make a predictive query that checks or that tries to predict whether a user will churn here, and we can represent churn here as not making an order in the next 30 days, for example. And this is our target clause. And so in the end, this predictive query language is like super powerful to express many different use cases, from recommendation, from classification, binary classification, regression, and so on, depending on either the entity table itself or many different fact tables. And so, as I said, if you want to impute missing values, then the target table and the entity table are the same. So we're predicting users' age, for example, based on their recent order history and so on. We can also predict aggregated future behavior. And so we're not limited here to a single target, but we can also write something like predict whether the count of orders is greater than 10, or the sum of all the order prices I'm doing in the next 30 days is greater than 100. And so this will be treated as a binary classification task. And then you can also refine predictive queries by adding filters. And so you can add filters both at the target table level, but also on the entity level. And so these filters basically define not only how the target table or like the targets are computed, but they also define what in-context examples should be used in order to make that prediction. So for example, here, we would be only interested in the orders where the price of that order is greater than 10. So that gives us like a restriction or like filters out the orders we aggregate here and use here as labels. But if we use these filters as entity filter, that means that all the in-context examples we generate are expected to have only include users with age less than 30. And lastly, besides like node or row level classification, you can also do recommendation or link prediction by using the list distinct aggregation here that links to a foreign key in the orders table. And that here means like predict all the item IDs a user will buy in the next 7 days. There exist different model options one can use here. And so in the end, what most people will want to use is the model.predict function, which takes in a predictive query. It takes in different run modes and different configurations, which I want to talk about later. But that gives you then a prediction back for a single entity or a subset of entities, which you can then use downstream to make a decision. There also exists an option to evaluate a query, and that gives you a sense about how good the quality is of the model prediction. And how that works is that we're kind of going back in time and collect test examples which fulfill this predictive query you write, and then compute metrics on top that give you a sense about how good that model behaves on historical data before you apply it on unseen data and making a prediction on that. And so you have different options here to tune the output of the prediction and evaluate functions. One option is the run mode, which basically is designed to trade runtime with model performance. And so by default, we're using like a fast run mode here, but you can also tune that. For example, best will use like a larger context, will use a deeper model. And so it basically computes or predicts for longer, but usually you get way better model performance that way. Another option you can tune is the num neighbors option, and that basically tells you how many neighbors you sample as part of your subgraphs for how many hops. So the length of this list here denotes like the number of hops we sample for creating subgraphs for entities and in-context examples. And the values of that list denote like how many neighbors or like the maximum number of neighbors we sample in each hop. There's another argument, which is the anchor time, and that is the time. So usually this is, or by default, this is kept blank, which means that we are making a prediction up to the current state of the database. But you can also go back in time. You can fix that to like a midnight timestamp and so on, whatever you want. Another option is the max PQ iterations options, which I'm just adding here for completeness. Usually that doesn't need touching, but it might be beneficial to increase that if you have a very restrictive predictive query that has like restrictive entity filters, and so we're unable to find sufficient number of in-context examples. And then the evaluate function also has this metrics argument that can be used to write or request different metrics for different task types. And so if you get started with KumoRFM, I want to give you like a few things to look out for. And so in the end, I don't want to get you to be overwhelmed by how you're setting up graphs and so on. So I think your main goal should be, if you try that out on your own data, to get to a predictive query as soon as possible with the smallest amount of tables necessary. And what I mean by that is that I'm seeing people, for example, directly adding 12 or 15 tables to your graph, and then they're kind of super struggling to see how they need to link these 12 different graphs together. But instead, I think the better approach is to start with a smaller set of tables, like whatever you feel is like the essential bits of tables you need to make that progression, to make that prediction, and then you progressively add more tables and see how model prediction behaves and so on. It's always good to double check the semantic types, especially because they define like how we interpret different tasks. So yeah, as I said earlier, if you want to predict users' age, that can be both regression or classification task, depending on the semantic type of the age column. So we provide like handy shortcuts to directly see which semantic types the column has in your graph, and you can change that quite easily. And then you need to make sure that the critical information for an entity to make a prediction is reachable within the number of hops you specify. And so if you have like a super rich signal table that is known to be critical performance, but it's like 5 or 6 hops away from your table, you have basically two options. One is you increase the number of hops and the number of neighbors you sample. The other option is to bring this table closer to your entity table. And I think both approaches are valid and need to be verified experimentally. And then lastly, only if you have a really working query, you're ready to like explore these advanced settings such as run mode and anchor time. But don't get too lost in all these arguments and options. Try to get to a predictive query as soon as possible. And so if you want to learn more, we also have this publicly available GitHub repo, which is under the Kumo AI organization, and it's called Kumo-RFM. And especially you want to look at these different notebooks we collected and will collect over time. So we have a quick start notebook. We have like the ultimate handbook on how to use KumoRFM that introduces all the different options. It goes over how you evaluate model performance with KumoRFM and so on. Now, we also have a predictive query tutorial if you feel that predictive query might be overwhelming to you. And we also have like a single tabular data notebook, which kind of shows you that you cannot only use KumoRFM to predict on graphs, but you can also use it to predict on single tables. But yeah, just want to point that out here if that is interesting to you. But usually KumoRFM is designed to give or like trained in such a way to operate on multi-table setups. And then lastly, we introduced two other notebooks here, which go over how to evaluate KumoRFM on the RelBench datasets and tasks. And so this mimics our results reported in the paper. And we lastly added a walkthrough on how to evaluate KumoRFM on the SOLT dataset, which is like a recently introduced dataset by SAP. This notebook goes over how to load in this dataset and evaluate KumoRFM and see that performance. And so this kind of concludes my session, and we're now basically opening up the beta testing session. And so I will kindly ask you to go over this Google Colab and try KumoRFM yourself. This Google Colab is designed in such a way that it introduces you to both KumoRFM and predictive query. And then you can execute that notebook, and hopefully it works for you. It should. You can fill out the blanks, so there exist a few cells here and there where we expect user input, and just try to try to get to the end. And so if you're doing that faster than before this webinar session here closes now, you can also go ahead and explore other predictive queries, make modifications to that graph, or test KumoRFM with your own data, and we are very curious to hear about your experience with that. And then lastly, I kindly want to ask you to complete this beta testing survey here, which is also linked in the respective Google Colab at the end. And so whenever you are stuck or you have basic questions around KumoRFM or Kumo in general, you can directly ask here in the Zoom session in the Q&A section, and we are here to help you out, answer questions, and discuss. And with that, you can go to this tiny URL, .com/RFM hands-on URL. We can also paste that in the chat, I guess. And so I quickly want to introduce you to this notebook. So I don't want to go over it in full length, but just introduce you to the main concept here. So it begins basically by installing the necessary packages, and then you need to authenticate and initialize Kumo SDK against an API key. And you can get this API key for free here. And then the dataset we're looking into is the Super Mario Maker dataset, which is from Kaggle. And so this is kind of like a playfully designed dataset to introduce you to the world of KumoRFM. And so this dataset contains players, and it contains game maps, and it contains rich interactions between these maps and these players, such as whether a player played a specific map, whether it liked the map, whether it completed or cleared that map, and so on. And so if you run that notebook through, that will go over the different data you have in that data set, it figures out like the different columns. It shows you some of the images of these graph game maps and so on. And so in the end, we can load this data in here, as you can see here. And then we are ready to put it into KumoRFM by creating this graph here. And then you can see that we infer different primary keys, time columns. We infer different graph links as shown here. And you can also visualize that graph to see how it structures the different table and connects them to each other. And then here and there you will see symbols like this, where it's like your turn, or you would see to-dos here, where we kind of expect you to make changes, like writing predictive queries or making changes to the underlying graph and so on, to get you familiar with that. And so to all of these to-dos here, we also provide a solution, but only look at that if you're feeling like super stuck. Because we want to get your honest opinion on how easy or like what are the frictions you have with KumoRFM. And then later on, this notebook goes over different ways how you can query or predict with KumoRFM. And we can see that we have different queries here prepared, which you can run and test model performance and so on. And with that concludes my talk or my introduction. We can keep this screen here. Thanks for your attention, and yeah, feel free to try this out and let us know your feedback, questions, and so on. Thank you.